All right, we'll get started here, and so I've posted your first homework assignment. You'll download the R Markdown template. You'll fill out the answers and render it as an HTML file and submit it under homework 1. Okay. The homework is intended to be done individually. Okay. You can talk to other students and discuss ideas, but you're not supposed to be kind of showing each other your code or the work that you guys are doing. Okay. The school in general is taking a stricter approach towards academic dishonesty issues in the kind of these programming fields. It's a long and painful process, so you know, it's best just to do your own work. And I want to say it's okay not to get 100% on your homework, okay? And I know it doesn't feel that way, and I know a lot of you feel like you have to get everything right on the homework and whatever. And of course, we want you to understand everything, but it's also okay not to get 100% on your homework, okay? And I would say it's better not to get 100% and to do what you are capable of, or you know, what you had time for, than it is to sacrifice your personal integrity or sacrifice your mental health or sleep in order to finish the assignment. Okay. Right now, I think this first homework assignment pretty much covers through cross-validation, which I got through a lot on Monday, and I'll wrap up today. And so you should be able to do quite a bit of it. The other stuff that I covered today, like gradient descent and shrinkage methods and regularization, those are not even covered in this first homework assignment. I'll probably get the second homework assignment up and running pretty soon. And just like everything else in life, it's better not to procrastinate. It's better to get started as soon as possible. And again, it's okay if you've done what you can and you get as far as you can go, right? Do the best you can. That's all I can ask for. Is there something else I wanted to say about homework? That's that. Okay. And please don't post your homework solutions anywhere online. Okay. Don't create a GitHub with all of your homework solutions on there. That just creates a bunch of headaches for me. And to be honest, employers, I know people think that, you know, this will like show off their skills or something to an employer, but an employer is not impressed if you tell them I did my homework and here's my homework. Okay, that's not impressive to anyone who's hiring. Okay, because that's what's expected. Okay, if someone says, why should I hire you, and you say, well, look, here's my homework, I did it, that they're not going to be impressed. Okay, if you want to impress someone, an employer, with a GitHub and stuff you've done, do something original that is that no one prompted you or told you to do. Okay, if you say, you know, I learned this in class and it was interesting to me, and so I found this other thing and I applied what I learned to this other thing, that's impressive. That shows initiative, that shows creativity, that shows original thinking. Okay, if you want to have a GitHub to show off to employers, that's what you should do. Don't say, oh, here's my homework. That no one's impressed by that. Okay. So anyway, I'm a big proponent of showing off work on GitHub, but homework's not the thing that you should be showing off. It should be stuff that you've thought of and come up with, and you know, related to class stuff that you learned. Yeah, that's fine. But that's that. Okay. All right. The Campus Wire link is here. You should be able to join. Alex created this playlist of my videos from last quarter in the spring when I also taught this class. And because it's the summer, sometimes I've got to like flip through some of these slides a little bit faster than what I would normally do in a full 10-week class. And so if something wasn't fully covered, feel free to access these things. I'm going to be making some modifications and stuff to the slides as things go on and stuff, but by and large, the content should be fairly similar, okay? Okay, any questions before we get started? Yes?
The homework due date.
Homework, I think I made it due next Wednesday. I try to give about 1 week for the homework assignments. There might be more than one homework going on at a time, so like the second homework might be assigned before the first homework's even collected, and I know that's not fun. It is a little bit of the nature of the 6 weeks compressed summer thing, so that's what we've got. Okay, let's see if I can do this and get this to, okay. All right, that looks about right. Oh, okay. Let's see if this online poll thing is working for you guys, and we'll just start off by taking some attendance. And I know I don't want you guys to be insulted by the fact that I take attendance, but I like having students here. I like the interaction with students. So anyway, we'll try this out. When I tried it with my Stats 10 class, some students complained that they were not able to see the poll, and so anyway, what you will do is you will log into onlinepoll.ucla.edu either on your phone or your computer. You'll need your two-factor authentication to log in. I imagine you carry your phone 99% of the time that you are out of your house, and so I don't imagine this being an issue, but you know, if your phone dies or something because you forgot to charge it, you know, you'll miss out on 1 day of the polling, okay? Just respond, any letter is fine, okay? This is to take attendance. You don't see it, okay. Other people who's not seeing it? That's a lot of you, okay. All right, well, but 9 of you saw it and responded. Okay, well, all right, well, we'll see what happens. I'll probably just throw away today's thing. I've also, the other class had similar issues where about half of the students couldn't see it, and so I reached out to the online poll group, see if they can fix the issue. I hope they get it fixed, okay? But we'll go from there. Okay. It should just be 102B, August 7, 2019, 1:10 p.m. Under onlinepoll.ucla.edu. If it's not appearing there, as soon as you log in, it should appear, and if it's not appearing there, then it's not there, okay? But some of you have seen it? 16 of you? Okay, so, all right, so maybe more than half of you can't see it. All right, we'll get started. This is week 1 Wednesday. This is like week 2 of the regular quarter, okay? So if you're like trying to match up stuff with what happened in the spring quarter, this is week 2, okay? This is just summer, right? Okay, so actually, yeah, it leaves off with lecture 2-1, okay. Okay, so we're gonna just talk about cross-validation again, okay? And so the idea with cross-validation is that we are trying to select a model, okay? So the traditional method that you've probably learned in your 101A linear regression course is that, you know, you look at the summary of coefficients and you see you test which ones are significant, and that's provided in that summary information. You're trying to decide whether you should use the model that includes this variable or the model that doesn't include that variable. You're trying to select which model to use. And you use things like the AIC or the BIC or, I don't know, whatever other criteria to decide which model is the best, okay? And that was your traditional approach. And oftentimes it required us to do some thinking. And kind of the machine learning way, whether for good or for better or worse, is that we take away some of this human thinking and we have the computer or the kind of the algorithm just say, like, let's fit a model and let's see how well it does in predicting. Okay? And what we want is we want a model that is able to predict data that it has not seen. Okay? We want to say this is data that was not used to train, not used to figure out what coefficients to use. It wasn't used to train the data, but it's still able to predict real data that we have. And in order to do that, we have to split our data into the training set and the validation set. Okay? And so we talked about leave one out cross-validation and k-fold cross-validation. And so we started off with just this very simple data set with 4 data points, and we did leave one out cross-validation, okay? And when you do leave one out cross-validation, you have to fit n different models, okay? So we have 4 data points, we got 4 different models. If you have 1,000 data points, you got 1,000 different models to train, and you find the cross-validation score. And so this is just kind of all 4 graphs put together, okay? So this is when you use these 3 data points and you fit the line, this is what you get, and this is the squared error on this point. When you use these 3 data points, this is the line that fits, and this is the squared error. When you use these 3 data points, this is the line that fits, and this is the squared error. And when you use these 3 data points, this is the line that fits, and this is the squared error, okay? So we get 1, 1.6, 1.6, and 1. And when we figure out the mean squared error, it's around 1.326, okay? And so this is the mean squared error value for a linear model fit to this data, okay? And the value isn't so much in this number all by itself, but the value comes from if we do cross-validation for a competing model, we will get another mean squared error value for that competing model, and we can compare these values across the competing models, okay? And I haven't done that per se, but this is kind of just an illustration. So we said, so when we fit the linear model, our cross-validation score is 1.326. We could try something like a log-log model or a, some different kind of model, and we want to say, like, is this model any better, right? So we'd go through the same process. We fit the log-log model 4 times. Each time a different observation serves as the validation set. We calculate the cross-validation error there, and we compare the scores. So just to kind of illustrate this with an example, we're going to go back to the Olympic data. Okay, and the Olympic data is we are trying to predict the winning race time for the 100-meter run when based on the year in which the competition took place. Okay, and so so we can try a linear model, a quadratic model, a cubic model, and then we'll go 4th order, 5th order, 8th order, and just for fun, we'll do a 17th order polynomial, okay? And we're going to see what is the total squared error for each model when we do the validation set, okay? And so for the purpose of illustration, I'm going to just do 1 training set and 1 validation set. So I'm going to do 4-fold cross-validation. So technically, for each model, I would have to train the model 4 different times. I would have to fit the linear model 4 different times using 1 validation set, 1 training doing this, right? So if I do this, I would have to fit the linear model using this training set, and then I would validate it. And then I would fit the linear model using this training set and then validate it. And then I would fit the linear model using this training set and validate it, and fit the linear model using this training set and validate it. Okay, and then I would also do the same thing with the quadratic thing. I would train the model train the quadratic model, validate it, train the quadratic model on iteration 2, validate it, and so on and so forth. And I would try out however many models do I have here? 1, 2, 3, 4, 5, 6, 7 different models. And I would do, 7 models on this training, validate, 7 on this training, and validate, okay? For the illustration, okay, you're going to just have to imagine iterations 2, 3, and 4 happened, and I'm just going to show you what happened during iteration 1, okay? So that's what we're going to, okay? So I'm going to be using the same training set and the same validation set, but we're going to do this for all of these things, and you can just kind of pretend that similar things are happening with iterations 2, 3, and 4, okay? All right, so here is our Olympic data again. What is this thing anyway? Did someone just take a pencil and scratch this? Okay. All right, so Olympic race running times have been getting faster over the course of time. Okay, I think. When did Usain Bolt do his first Olympics? I don't know. Who's the fastest man on Earth right now? Is it, huh? All right, anyway, okay. Look it up. We'll ask Google. Huh? 2008. 2008, so maybe he's in this data set, okay? Let's see. World record 100-meter race. I don't know. Okay, current men's world record is 9.58 seconds by Jamaica's Usain Bolt, 2009. And the women's world record of 10.49 seconds by American Florence Griffith Joyner, 1988. Wow, that remains unbroken. Okay. All right, so this is what we'll do. I think I showed you this. We've got 28 observations. We shuffled them up. We put 7 into set A, 7 into set B, 7 into set C, and 7 into set D. And we'll skip this. And here we're going to store all of our total squared errors in here. And there's because we're fitting 4 iterations, we're going to find the squared error for each iteration. So each one will have 4 different of these things, okay? And do I want to go through this line by line? I don't know. Not really, but we'll talk about it. Okay, so basically I take the set, okay, and then, using your double bracket notation when you're subsetting a list, okay, we extract those indices, and I say this is our training index and this is our validation index, right? And so basically, just imagine we got values like that in one of these v-index things, okay? And then we create our training set and our validation set, and using that, I fit our first model. I say linear model, predict t based on x using the training data, and that produces the model. And R makes this really easy for us. So now we have a model, and we can just do predict based on that model. And we're going to predict it for the validation set, okay? And that gives us our t hat. And now we can calculate the squared error by taking the actual data, the validation data's actual t values, and subtracting off the predictions, the t hats. Okay, we take that difference, we square it, we sum it up, divide by n. Okay, sound good? Okay, and we do the same thing here. Now I have linear model. We're predicting t based on a second order polynomial using the training data. We use this model 2 to make predictions, and we call this t hat 2. We take the differences, we square them, and we divide by n. Okay, and I just do this for model 3, polynomial order 3, order 4, order 5, order 8, order 17. It's like hard to read, but it's basically the same thing, just done over and over again. Okay, so this is what one training and validation set looks like. Okay, so there's technically 4 of these kind of training validation set combos, but we're just going to look at this one here. Okay, so we are going to train on the black and white circles, okay, and then the red dots serve as our validation set. Okay, so we're going to fit a line using only the black and white dots, and then we're going to see how well did the line we fit using the black and white dots predict the red dots? Okay, so I'm going to make the red dots disappear. Okay, I make the red dots disappear, and this is the best fitting line on our training data. Okay, all right, and now I will make the red dots appear and the black and white dots disappear. Okay, and so now we can measure the error based on our model that we fit. We can calculate the validation error. Okay, so again, we hide the red dots, we hide the validation, and we fit our model. Okay, and then once we have the model fit, this line remains the model that we're using, and we see how well did it predict the red dots. Okay, and so we can see this one, it did a very good job predicting. Okay, and this one, it also did pretty good job. Okay, and there was some error here, and there was some error here. Okay, so anyway, we take the mean squared error on this validation set, and we get 0.0319. So we take all of this and we divide by how many we have, and we get 0.0319. Okay, all right. So I guess I can go back to here. So again, going back, so from here, we fit the line, best fit line, just on the training data, and then and this is the best fitting quadratic model. Okay, and then we say, okay, well, how well did it predict the red dots? Okay, and so for the red dots with this set, so we trained it on this, and we're testing it on this validation set. Okay, the mean squared error, if I look at the average error here, is 0.025. Okay, so we're getting slightly better cross-validation. So this versus this. Okay, so the red dots remain in the same location, but the blue line has changed, right? All right, and so we get slightly different mean squared error. Okay, all right. Now we'll do the third order polynomial. So again, we're fitting it just to the training data. So this is what the fit on the training data looks like. And then we say, well, how well did it predict the red dots? And this is what it looks like here. Okay, so again, the location of the red dots is the same, but the fitted line changes. And it turns out when we use the cubic model, the third order polynomial, the mean squared error validation is even lower at 0.0131. Okay. All right, and we just keep doing this. So this is it for the fourth order polynomial. Okay, so this is the best fitting fourth order polynomial to fit this thing. We say, well, how much error is there? And we get something like 0.0192. Okay, here it is for eighth order. So with the eighth order polynomial, now we're able to fit kind of these extreme values up there. We're really trying to minimize the amount of error that we get in our training data. Okay, and we say, okay, well, how much error is there when we predict? And we can see, because of the eighth order polynomial, we get this, slightly weird thing going on towards the end, right? So with the eighth order polynomial, they like rapidly shoot off in different directions once you kind of go off to the sides. And so we can see, in our validation set, this is probably inducing a little bit more error than it really should. Okay, and then just for crazies, we did the 17th order polynomial. Okay, and we can see this is not a good fit. Okay, but technically it is, right? So if we looked at the amount of error on the training data, there's actually very little error on the training data, right? It's like predicting these 3 points perfectly. It predicts these points, perfectly right here, okay, or very close to perfect. And yeah, there's a little bit of error there, but overall, just the amount of difference between the line that we fit and the training data is very, very, very small, okay? But then we say, okay, well, how well does this predict the data that was not in my training data? And we can see it's really bad. Like, right, this guy out here, the prediction is like, I don't know, past the ceiling here, and so there's a crazy amount of error, and so the average is 1,640, okay? Where everyone else is like 0.03 and 0.02. This is now this ridiculously huge number, right? And we know that like it doesn't make sense, right? That because we're talking about like how has Olympic race times improved over time, and we're basically saying we got really, really fast in the year, I don't know, 1997 or something, and then in the year whatever 2001 it was slow, and it doesn't make sense. Okay, so this is obviously a bad fit, and the validation, you doing cross validation with the validation set kind of supports that. Okay. Okay, and so anyway, I showed you, I think we did validation set C, okay, and so we saw things like 1640 and 0.0319, 0.025, 0.0131, 0.0192, and stuff like that, okay? So this is, but there are technically 4 validation sets that we could have used, okay? I said we had 4 iterations, right? So we're at slide 28, where are we? Okay, so so I guess we only saw this one, iteration 3, where we're using set C as the validation set, but we didn't really see the graphs for iteration 1 and iteration 2 and iteration 4. We didn't see those, but I calculated those, okay? And for the linear model, our validation error was around, 0.02, 0.025, 0.03, and 0.1896. This is probably validation set D is the one with that 1896, which is like way off from everywhere else, and so you just have a lot more error there. Okay, and so anyway, your average cross validation score is something around 0.0674. Okay, and then with the quadratic model, we get slightly different values each time we run it, and the average of these 4 is 0.0624. Here's the third order polynomial fits and their cross validation errors, and we get something different, right? Okay, and so when we take a look at these averages, okay, we get an average of around the lowest value that we see for the average cross validation score is 0.0571. Okay, so according to this, the third order polynomial has the lowest kind of cross validation score, and so this would be the model that we would probably pick based on our 4-fold cross validation. Okay, yes.
So once we've used the cross validation to determine which type of model we're going to use, when it comes to finding out which parameters we're going to use in that model, do we just run it with all of the data, or do we run it with a specific subset, or how?
Yeah, so probably you use the cross validation to kind of decide which model to use, and so now we're just going to say, okay, we're going to use this third order polynomial, and then yes, you'd probably train it using all the data that's available to you. Yeah. Yes.
Why are we using the third and not the eighth? If the eighth is 0.4.
Oh, you are right. So this, okay. Okay, so if we use strictly the cross-validation thing, okay, without using any thinking, all right, we would go with the 8th order polynomial, right? But if we just kind of step back and think a little bit and go, which model is the best, probably the 8th order polynomial, at least if we think about it, doesn't quite make sense, right? So I guess this is captioned wrong here. So yes, if we don't do any thinking, we would go, oh, the 8th order polynomial. However, the fact that this is 0.0419 could also be just a coincidence of the validation sets that I've used, right? So when you do a 4-fold cross-validation, we randomly split the data into 4 different folds, okay? And if somebody else did it, they would get 4 different folds, okay? And so I think, okay, so I think I did this to address that, and I just kind of captioned this wrong, okay? Or maybe, okay, so here, so yes, I should modify this. This is 0.0419, which is technically the lowest. And so if we weren't thinking about it, we might go with this, okay? Based on our intuition, this doesn't feel quite right, okay? And so if I just did a re-randomized the validation sets, okay, where I have 4 different things, I get similar but different results here, right? So now the third order polynomial is the lowest, and as we would kind of expect intuitively, the 8th order polynomial does worse, okay? Because something in us says, you know, it doesn't quite make sense that there would be an 8th order relationship with whatever's going on. You know, probably even the cubic relationship doesn't quite make sense, but maybe that's a little bit more reasonable to understand than the other stuff, okay? And at least via cross-validation, that conclusion seems to be supported, okay? Yeah.
Just curious. So if, like, say the 8th order performs better under like a specific bound, could you just turn your model into, like, say, from like x equals like the year of 1997 to like 2000, it follows the 8th order, and then after that it follows the 3rd order?
Okay, so yes and no. So the question comes down to, as always, what is your goal, right? What is your goal? And if your goal is to just kind of infer what happened, like you create a thing and you say my model performs best for the data between 1990 and the year 2000, this decade. I lost my train of thought. Okay, between for this decade, 1990 to 2000, this is where my model performs best. Maybe that's fine, okay? But a lot of times you want to be able to predict something where maybe you haven't quite collected data yet, okay? Or maybe you just want to be able to say, like, okay, I got 1990, 1991, 1992, something happened in 93, I didn't get that data, but then I got 94, 95, 96, and 97. So just to figure out 93, we're gonna use some model to guess that. Maybe that's fine, okay? It could also just be like, well, and this is always dangerous when you do regression, but you can say, like, okay, this is what has happened up until 2019. Can I predict what will happen in 2020 or 2021, okay? And I would really hesitate to make any kind of predictions even more than a year away, because who knows what's going to happen, right? Like, we can predict maybe a little bit like what kind of phone we'll have this year, but what will phones look like 5 years from now? I don't think anybody has any idea, right? So like what apps will be popular? I don't know, right? Phones are crazy, so most people are too. So I guess the question is always, what's your goal? What's your goal? And if your goal is to just have a limited range, then sure, that's fine. And if your goal is to have something a little bit more general, then maybe that's not good, right? So there's always considerations to have. Okay, does this kind of make sense for what's happening there? Yeah.
So once we run through the cross-validation, get these rough scores.
Yeah.
Because you did mention our final results and which one is considered best according to cross-validation can depend on, however data is split.
Mm-hmm.
Would you recommend running it a couple times off different seeds just to make sure that doesn't happen?
And the answer there is how much time you got, okay? And if you have the computational power to do it, sure, that's totally fine. If it's not super expensive to run the thing and do it again with a different seed, yeah, that's great. Okay, and that's going to probably give you a better sense. You might be fitting like this really complicated thing with a huge amounts of data, and I don't know, And the question also comes down to, like, how big is the difference, right? Like you've got two competing models, and maybe they're quite different, but like as far as their prediction performance goes, maybe they're very similar, and one's just like ever so slightly better than the other, and you're not quite sure, right? Like, we're not going to really cover this stuff, but like, let's say you're like considering like XGBoost versus some neural network, right? And these are like very computationally expensive and whatever models, you know, and maybe you do cross-validation and the performance of both are very good. Maybe one is ever so slightly better than the other. Then there's probably other things that you want to take into consideration. Just like which one's easier to implement on a larger scale, right? Which one do I understand more? And like if I run into a problem, I can fix, right? Say, because you might understand one of these things, but not the other one very well, right? And so actually, do you guys know about the Netflix prize? Netflix. So you guys know Kaggle, right? And so Kaggle has competitions that are often sponsored by companies, and whoever performs the best will get like some kind of bounty that the company sponsors. It will be like $10,000 for the best model that predicts all of these things, right? Well, the Netflix prize, I would argue, was the first major data science competition sponsored by a company. Okay, and so this was like, when was it? 2009 or something? This was before data science really took off. And I would say this was one of the big catalysts in making data science popular and causing you guys to all want to major in statistics today. Was Netflix says, so right now when you go on Netflix, it'll have like 87% match or 94% match. But it used to have stars. It used to be like, this people rate this 5 stars or 4 stars or 3 stars. And how do you rate this, right? And they wanted a way to kind of predict how people will rate movies, right? And so if you were like a fan of horror movies, you would rate like The Ring this many stars and all of these scary movies this many stars. And if you didn't like horror movies, you would probably rate those movies like very low, right? And if you like children's movies, you know. And so they wanted to be able to predict this stuff, and they had this huge data set, and they said $1 million to whoever can improve our current prediction algorithm. So this is our current prediction algorithm. This is how well it performs. $1 million to whoever does it best. Okay, and that was a lot of money, and a bunch of different people competed, and universities competed, and stuff like that. And there was a winner, and they got the $1 million. And you know what Netflix did? They said, "Oh, this is awesome, but it's too complicated to implement, so we're not even going to use it." So that's what ended up happening. So stuff like that happens. You can get a model that does really good, but it might be too complicated to implement, and you just have to do something that's just okay but easier. So anyway, a little story there. You can look up the story. Search Google for the Netflix prize, and there's all sorts of interesting stuff. A lot of backstabbing and stuff too. Whenever you have money, there's backstabbing, right? So, not whenever. Okay. Oh yeah. Wait. You know, this is one of those weird things. Okay, so something happened. Okay, I'll have to go back and fix this, but I think I have the caption wrong. So it says, with this thing, the 8th order polynomial happens to perform the best, which is not the case in this thing. And so this is just a coincidence of the values that ended up in the validation set. Okay, so based on the other cross-validation we've done, we know that the 8th order polynomial is not the best. I have the captions and the tables slightly mixed up. Okay. Okay. You can do cross-validation with library boot. I think I showed this briefly on Monday, but here I've got some slides again. And so I think by default, it's going to do leave one out cross-validation. Okay, so you fit GLM to fit a model. And GLM, for right now, for our intents and purposes, GLM works the same as LM. Okay, obviously it does things differently because you can fit logistic regression models and stuff like that. But for now, we can treat it as if it's fitting a linear model. And then you can do cv.glm to do the cross-validation, and it's going to provide a score, okay? And so so here we can run this here. And so using this, I'll do predict time based on first order polynomial, basically a linear fit, okay? And then you do cv.glm using, here's the data, and using the model, and you can say I want four-fold cross-validation, okay? And you can run it 3 different times and you're going to get different values because of the random nature of this four-fold, k-fold cross-validation, because of the random data that ends up in this data set versus this data set versus this data set, right? Okay. Here it is with the quadratic polynomial fit, okay, poly 2, and you run four-fold cross-validation and we get slightly different numbers. For a third-order polynomial, we get different numbers again, and so on and so forth. Okay. What happened here? So here, when I have k equals 4, there's randomness regarding what kind of, who ends up in which validation set, right? So on this one, like validation set 1 had these observations, and then in this one, validation set 1 had different observations. So we're getting different values. If you don't specify k equals 4, it's going to default to leave one out cross-validation. And so if you do leave one out cross-validation, then every observation has a turn to be in the validation set and its own validation set. And so the leave one out cross-validation ends up being identical no matter how many times you run it, okay? So there's no randomness that plays a role here. You get the same value here, okay? So that's a nice feature of leave one out cross-validation, but again, it usually takes a little bit longer to run because of you got to fit n different models, okay? There's actually some mathematical shortcuts that avoid this if you're doing just a strictly polynomial fit or a strictly linear model fit, but I'm not going to get into it. Okay, so cross-validation is a method to see how well a particular model will generalize to new data. The goal of cross-validation is to test the model's ability to predict new data that was not used in estimating it, and multiple rounds of cross-validation are performed using different partitions. Okay, so we got that. Okay, so now we will talk about computational methods that we can use to optimize the loss function. Okay, so this is now a different topic, a different day, a different lecture, but here we're trekking through. Okay, all right, and so far we've been using calculus. All right, so this is we've been trying to reduce the squared error, the kind of the RSS of our model. We're saying, you know, the actual value is t sub n. Our model predicts f of x sub n, and we're going to square that model and we sum that up, right? Or 1 over n, so we get the mean squared error. So this is how we do it, and we're trying to. When we said let's minimize the mean squared error when we train our model. So when we're doing linear. Fitting a linear model, we want the coefficients beta 0, beta 1, beta 2, whatever, so that this value is minimized. Okay, and we did it with calculus. Okay, we wrote it in matrix notation, and we said let's take the derivative of this with respect to the w parameters. Let's set that equal to 0. Solve for what w should be. We got x transpose x inverse x transpose t. And that's what we got, right? So we said this is how we're going to minimize the thing, and we did it with calculus, right? What we might do is that sometimes it can get complicated and we can't take the derivative and set it equal to 0, okay? Like the math can get really hard, right? Taking a derivative of a complicated function, maybe that's hard. Setting it equal to 0 and solving might be even harder, okay? So we can use some computational methods, right? And so, so this is, we create a function and we're going to treat the data that we have observed as fixed values, okay? And this bug is torturing me today. And now we have a function of the parameters that go into it, okay? So for linear regression, we have two parameters, the slope and the intercept, and we want to find the slope and the intercept that does the model best. For a higher order polynomial or a more complicated model, we may have more parameters to do this, right? In 102A, I think you guys covered coordinate descent, right? Or did you guys not cover coordinate descent? Okay. And here we'll discuss gradient descent, okay? Similar but different. Okay. And so we've talked about the gradient, which is basically the derivative of a function, but with respect to a vector, okay? So we're taking the gradient, which itself will be a vector, okay? And so it's the derivative with respect to a vector, okay? And that's going to be the gradient. And the gradient itself is a vector, and it points in the direction of the greatest rate of increase, okay? And so gradient descent, the algorithm says, if you're standing on some surface, okay, and we're imagining this surface has a low point, like a valley, okay, and we want to get to this bottom, right? If you're on the surface, the low point represents the minimum. We want to get down there. The way we are going to do this is, wherever you are standing on the surface, find the gradient. The gradient points uphill. The gradient points in the direction of the steepest increase, and go in the opposite direction. So say, that way's uphill, I'm going to take a step in the opposite direction, take a small step, recalculate the gradient, and you say, okay, which way is uphill? And you take a step in the opposite direction. And that should always get you downhill and hopefully get you to at least a local minimum, okay? And so that's the idea, okay? Gradient descent's not guaranteed to work. There's all sorts of issues, but from a computational standpoint, it's a very simple idea, and it's also easy to implement, okay? As assuming we can find the gradient easily, right? That could be the hardest part. Okay, and so this is what the gradient descent algorithm looks like, okay? This is your current location, okay? So again, our function is a function of the parameters w, okay? So w is w0, the intercept, and w1, the slope, okay? And we combine those together in the vector w, okay? So vector w sub n, this represents the current values of our slope and our intercept, okay? And then this is nabla, okay? This upside down triangle. Looks like delta, but the upside down delta is called nabla, okay? Nabla f of w, this is the gradient, okay, at that location, okay? And this thing, gamma, okay, this just represents some kind of scaling thing, like how big of a step? Are you taking huge steps, or are you just taking like little baby steps, okay? And so we just say the next values that you're going to use, the next values of w, the w's at time n plus 1, are your current values minus basically moving in a step opposite the direction of the gradient. Okay, and this is the entire gradient descent algorithm. All right. All right, so let me just try to show you some pictures. Oh, question.
Yeah, how do we determine gamma?
Yeah, that's a hard question. Okay, I know you didn't think it was going to be a hard question, but I don't know. Usually you start small, and then small is slow, and see, well, I say I want to go faster, and you try to go faster, and then you go faster until it breaks, and then you go, okay, well, that was too fast. So, yeah.
Is this something where we're going to need like a procedure to derive it, or in our code, are we just going to like play around and see what works?
Yeah. Probably just play around and see what it works, okay? Some people have done work to try to figure out the best gamma, but it's like, for all but the simplest problems, there's not an easy answer, okay? And we'll talk about the effect of gamma, all right? It's a good question, and it's a fair question. I just don't have a good answer to it, right? Like, How did we pick 65 miles per hour to be the speed limit on the highway? Oh, I'm sorry. That sucks, right? Right? So, I mean, like, you know the answer?
Yeah, it was fuel standards.
Is
Fuel standards is right. The highway might be safe. It's probably just fuel standards. They wanted us to save gas.
Well, you're most efficient driving around 50 miles per hour. And then the faster you go and stuff, I don't know. So, but I think, not that the lawmakers are playing around with our lives, but they're like, oh, 65, okay, that sounds good. 70, oh, that's a little bit fast. We'll do that in Texas. And 80 miles per hour, oh, no, that's too fast. I don't like that, right? I don't know, you want to go as fast as you can generally, but a lot of times going too fast will break things, right? So they don't even have speed limits in Germany. And that's because of the auto industry in Germany is so influential in the lawmaking. Just like every other capitalist democracy, if you got money, you can sort of make laws your own way, right? So the auto industry says, well, what's the point of us making these fast cars if we can't even drive them that fast? So just make sure everybody gets okay, well, all right. Anyway, let f be an arbitrary two-dimensional function. Okay, so I just made this up because I think I saw this example somewhere. And so this is what the gradient is, basically. The gradient of f, okay, with respect to x1 and x2 is going to be the partial of f with respect to x1 and the partial of f with respect to x2, okay? So this is some arbitrary function of x, okay? When we do things like optimizing a linear model, it's not going to be a function of x, it's going to be a function of w0 and w1, okay? But this is just a general function of x, okay? It's the partial with respect to x1, partial with respect to x2. So this itself, okay, x is a vector of two dimensions of x1 and x2, and the gradient of f itself is a vector of two elements. It's the partial with respect to x1 and the partial with respect to x2, okay? So this itself is also a vector of two elements, okay? And so it's important to remember that when you have a function of x and x is a vector of 2, the gradient is going to have the same dimensions. It's going to be another vector of 2, okay? So the gradient has the same dimensions as the original vector, okay? And so what is the partial of this with respect to x1? This becomes x1 squared becomes 2x1, minus 2x1 becomes minus 2, minus 0.5x1 x2 becomes minus 0.5x2, and then this zeroes out. Okay, so that's the first element. And then the second element, when you take it with respect to x2, these zero out. This becomes minus 0.5x1, and this becomes 5x2. Okay, so we have a vector of two elements, and those are the things. Is that okay? All right. Here's a contour plot of this function, x1 squared minus 2x1 minus 0.5x1, whatever. Okay, so this is what it looks like. It's a bowl. Okay, it's there. Paraboloid. That's the real name for it. Okay, not a bowl. It is a bowl, but a parabolic bowl. Do they sell parabolic bowls? Okay. Anyway, this is what it looks like when you graph it. All right, and if we wanted to do this manually, which maybe I'll ask you to do on a test one day, we would say, okay, well, here is the partial derivative with respect to x1. Here's the partial derivative with respect to x2. Let's figure out what the gradient is at this location, negative 5, comma 4. So we plug in x1 and x2 at negative 5 and 4. We get negative 14, and we plug it in over here, and we get 22.5. Okay? All right, so remember, this is what we're doing. We take our current location, and we subtract off gamma times the gradient, okay? So we said the gradient is negative 14, 22.5. So let's say our gamma is 0.1, okay? So at time 0, we're at negative 5, 4, and we're going to subtract off gamma of the gradient. So we're going to subtract off 0.1 times this, okay? And we do this, and we get this. Yes, question?
So I wanted to pay attention, what is WN supposed to be?
WN, what?
Well, what is it supposed to be finding? Like, are we optimizing for f prime equals 0?
Yeah, we're just trying to, no, not f. Yeah, I guess we're trying to find where the gradient is 0. We're trying to find the minimum of the function, and that's going to be where gradient is equal to 0. But we're doing this iteratively just by saying, where are we on the function? We'll take a step in the opposite direction of the function. And if we keep doing this, this will eventually take us to the minimum, okay, or a local minimum. Okay, and so if we do this, we started off at -5, 4, and at our next iteration, we are at -3.6 and 1.75. Okay. If I wanted to do this in code, I can do this, right? So the gradient of f will take in our current location, x1 and x2, and it will return a vector of 2 elements, where the first is the partial with respect to x1, and the second is the partial with respect to x2. And I've called that df dx1 and df dx2. Okay. Yeah, another question.
The gradient equals 0, does that mean that it's a vector of zeros?
No, we're not solving for where the gradient is equal to 0. The whole point of this is so we don't have to do any math to solve where the gradient equals 0. We're doing this iteratively to get to a location where the gradient should be about 0. Okay, so this is so just computationally, this is how we can do this, okay? And so I plug in -5, 4, and it says here's the gradient, -14 and 22.5. And then I say, okay, here's this is my starting location, I'm going to subtract off gamma times the gradient, okay? And when I say if gamma is 0.1, then it tells me, okay, your next location, if you're starting off at -5, 4, your next location is -3.6 and 1.75. And we would graph this by starting off at -5, 4, and we end up at what was it? 3.6 and 1.75. Okay, and then we can repeat this, all right? So now I'm at -3.6 and 1.75. I calculate the gradient at this location, all right, which is this. And then we take this value and we subtract off gamma, 0.1 times this, and it says, okay, our next location is going to be this, -2.5925 and 0.06950. Okay. You might want to just double check that this math all makes sense, right? And so if I plot that, this is my next location. So it seems like we're going downhill, okay? And so I will throw this into a loop, okay? Because I'm just doing the same thing over and over again, all right? So I'm going to just say, all right, let's do this into a loop. Each time, I'm going to take my current location, subtract off the gradient times gamma, okay? Gamma times the gradient at that location, and update the location, and then we'll store that in there, okay? And so we'll do this. We run the loop, and then I plot all of the arrows, and this is what we get, okay? So I started here at -5, 4. I took a step to -3 to -3.6, 1.75, and this was somewhere else, and this was somewhere else, and we can see, oh yeah, that is getting us to what looks to be the minimum, okay? And that's 20 iterations. And you can see that as I'm going down the hill, my steps get a little bit smaller, okay? Because it's like less steep. Okay. All right, so this is what happens when we choose different gammas, right? So I picked this gamma of 0.1 because I had played around with it, okay? But what happens if gamma was smaller? So here's gamma at 0.03, okay? And so my steps are smaller, and yes, I'm moving in the right direction, but after 20 iterations, this is as far as I got, okay? I need to run it for more iterations to get something closer to the real minimum, okay? At 0.15, I'm taking bigger steps, and so I get to the minimum a lot faster, okay? Here, I've taken gamma of steps 0.3, okay? So I'm taking really big steps, and what's happening is like, I've taken such a big step that I've gone past the lower point and I ended up on the hill on the other side, right? So it's starting to go uphill. And so right now this is okay, and I end up I still end up getting there, okay? But we can see this is probably not ideal, okay? And if I take gamma even bigger, then it can escape. So it can end up like you're on this part of the hill, and you've taken such a big step that you end up on the other side of the hill, or the other side of the valley, but you end up on the steeper side of that valley, and so your gradient is even bigger, and then so you just end up climbing the mountain the wrong way. Yeah, question?
So 0.5 is probably too big for all functions, or not?
No, it's different for every function. So there's...
How is that determined based on the function?
Yeah, I thought I answered this. The answer was, okay, well that's your bet. The answer is it's hard. It's hard to know exactly what size gamma to use, and I don't have good guidelines right now. You just kind of play around with it. You start small, and you keep cranking up the size until it works well. And if you crank it too big where it breaks, then you know you've gone too far. Okay. Yeah. For simple things, maybe there's a way to derive it, but for most complicated things, there's not a good answer. That's an active area of research, is learning rate, how to select a learning rate for your machine learning algorithm. You can look that up and you'll find a bunch of stuff and people arguing. Okay. Gradient descent for ordinary least squares. Okay, so here we're going to apply this for just ordinary least squares. And again, for ordinary least squares, our function, our loss function, which is the mean squared error, can also be written in matrix notation this way. All right, we've got the true values minus the data times the W, right? And right now, our W is a vector of 2, W0 and W1. Okay, it's got the intercept and it's got the slope. All right, and so I think we can do it this way analytically. Okay, we can take the derivative or the partial derivative of the loss function with respect to W0, and we get this. Okay, in non-matrix notation if I'm dealing with the sums. And you'll just have to trust me on this. Okay, you can go through and double check my work. Okay, but I don't feel like going through this right now. Okay, that's fine, right? You guys took your multivariate calculus class and all did great, I'm sure. No, I don't know. So that's not a jab at you guys. And here it is. You can take the partial derivative with respect to W1, the slope, okay, and you get something like this. Okay, I think I did this right. Okay, and if we did it in matrix notation, we get this. Okay, and I skipped a bunch of steps here. The full work is on like the previous lecture's notes to go from this step to this step. Okay. Okay, so the gradient descent algorithm, if we are not using matrix notation, is going to be you take your current values of W0 and W1, and you subtract off gamma times the gradient, which is the partial with respect to W0 and the partial of the loss with respect to W1. Okay. In matrix notation, it's your current values of W at time n minus gamma times the gradient of f of your current value W sub n. Okay. You don't feel like you have to copy all of this notation down. Okay. Just stick with me in the concepts of we're at our current location, we find the gradient which points uphill, and we take a step in the opposite direction, scaled by some learning rate gamma. We're just trying to go downhill, okay? That's all it is, okay? they say, I'll meet you at the bottom of the valley. And how do you get to the bottom of the valley? You walk downhill, and you keep walking downhill, all right? That's the gradient descent algorithm, okay? And if you're not sure which way is downhill, look which way is uphill and go in the opposite direction. That's what we're saying, okay? All right, so how do we code this algorithm? Okay, so this, did I even graph these? Okay, so here, this is just for the sake of this, okay? I start off with 3 points, 1, 3, 5, 4.8, 11.3, and 17.2. They look like they are in a straight line, but they're not exactly a straight line, okay? And I can plot them, but they look like they're in a straight line, but they're not exactly such, okay? And then if you did LM and you find OLS, the best answer is 1.8 and 3.1, okay? That's the slope and intercept, or the intercept and the slope of that we should use, okay? So here is how we figured this out, okay? So I have a function to calculate the gradient of the loss function, okay? And what is that? The gradient, okay? So if I take the derivative of this, the gradient is equal to this, okay? It's negative 2 over n x transpose t plus 2 over n x transpose x w, okay? And I think I got rid of the 2 over n parts because that's just a constant that scales it, okay? So I think I just have negative x transpose t and x transpose x w. Okay, so that's what I have here. Negative x transpose times t plus x transpose x times w. Okay, so that's the gradient. Is that all right? This line here. Students often, when they review the notes, they forget what this code line stuff says. Okay, so this is a function that just implements like finding the gradient at your current location w. That's all I'm doing here, okay? So we have the w vector, and we do this, okay? And then, and so here I'm using a gamma of 0.02. I just decided to start small, okay? And I just start at an arbitrary starting location, okay? The best slope is 3.1, and right now I'm starting off with a slope of 1.5. And the best intercept is 1.8, and right now I'm starting off with an intercept of -1, okay? So these are just bad, like, the data looks like this, and the best, this is supposed to be a straight line, okay? It looks like this, right? This has a slope of 3.1, okay? And right now, I don't know if you guys can see on that side, right now I'm using a slope that looks like this, 1.5. It's way too shallow. My intercept is too low. So right now I've got like huge amounts of loss, okay? And so what if I said, well, how do I make this line better? You would tell me, make it steeper, right? You would say, okay, the slope can't be 1.5. It's got to be steeper than that. So maybe, because I'm like too cautious and I don't want to increase my slope too much, maybe at the next iteration I'll try a slope of 1.6, okay? Because I'm very adventurous like that, right? And we try 1.6 and we go, oh no, that still sucks, okay? We got to make it even steeper. Okay, so I'll go 1.7, right? And we keep increasing the slope, and then finally, and at some point we get the slope kind of right, and we're also improving the intercept at the same time, and eventually we're gonna do this. So I run this 1,000 times, okay? Starting off at this terrible, bad intercept and bad slope. And all I'm doing is say, well, what's the gradient of the loss? Which way is it going to improve? And we just incrementally improve this. This is the entire gradient descent algorithm. Take your current W's and just change it by the gradient and update it, okay? And after 1,000 iterations, I'm at 1.7995 and 3.1001, which is kind of close to, kind is a relative word, kind of close to the true answer of 1.8 and 3.1, okay? And that's about all we can hope for in a computational method, okay? We don't know, we didn't bother solving for where it is equal to 0, where the gradient equals 0. We just said, well, let's just keep walking downhill, all right? And that's all we did, okay? So this is just some commands to plot the contours and plotting the gradient descent path, okay? And this is what the contour thing looks like, okay? So it said, you know, I started off here with a intercept of -1 and a slope of 1.5. And so early on, we rapidly said we've got to increase the slope. We got to increase the slope quite a bit, and then we were refining this, okay, to try to improve this, and this is what we got, okay. And this represents the lowest OLS solution, okay. So here, right here, this is my intercept is -1 and the slope is 1.5. These are the 3 dots, okay, and you can see that this is the current fit, and we can see this is really bad, okay. The next iteration, we said, all right, let's bump up the slope to 2.3, and so this line gets steeper, okay, and let's change the intercept to be something like this, and this is the line and the fit, okay. At the next iteration, the slope is now 3.3, and so already we're doing a lot better than what we started off with, right? Like this line is terrible, and after 2 iterations or a couple iterations, we're doing a lot better than we were before, okay? And we've changed the intercept and the slope, okay? And then so at this point, now it's just kind of like wiggling the line around, okay? So here, you know, I don't know how many iterations this was, but after a bunch of iterations, like we're getting something kind of close to the real thing, okay? This is the slope is almost right and the intercept's almost right, and we can tweak things, adjust things a little bit, and that's what we get. Okay, this is the effect of using the wrong size gamma, a gamma that's too big. We end up, again, overshooting, and we kind of wiggle back and forth. We still kind of get towards the answer, but this is probably not the path that we want to take, okay? And if I use a gamma that's too big, I end up with major issues, and I don't even get the right thing, okay? So this is also no good. So we want to do we want to get the gradient, and we did that earlier here. We did this vector calculus to get this thing, right? But you might also say, man, that was hard, right? You're asking me to take the gradient, take the derivative, do some calculus and get this? That's hard. I don't know how to do that, okay? So so we have something called numeric gradient calculation. This is not ideal, okay? This is not ideal. But it's a way to do it, okay? It's a way to do it, and it's a very useful tool, especially if, I would say it's most useful because ideally you want an analytic solution for the gradient, okay? So that should be your goal, okay? But when you do things mathematically and analytically, you're never sure if your answer is right, okay, right? Like I say, take the derivative of this thing, right? And aside from a test where somebody grades it, right? Like you're out in the workplace and you say, here's my function. I've got to take the derivative of this. I've got to take the gradient of this. It's this complicated thing. You do it and you say, well, did I do this right? Who knows, right? You're the expert in your department. And so you say, well, Tim, can you check my work? And he goes, I didn't take calculus. I don't know. So now you're stuck and you're just like, how do I know if I did this right, right? Are you going to go on Stack Exchange and ask somebody to check your homework for you? So this offers a solution, and we've got an inefficient tool, okay? You don't want to do this in a production environment. It's slow, okay? But you'll get an answer here, okay? That you can be sure is pretty close to correct. And so you can do this, and you can say if the answer you get here matches your analytic solution, then you can be confident that you did your analytic solution correctly, okay? If it doesn't match, then you go, okay, I got to go back and fix my analytic solution, okay? And so the way this works is kind of like when you take the derivative, right, and you take the limits. You had to do this in high school or something, right? And you just say like, okay, well, let's just try adding 0.0001 to x, and we'll see how much it changed, and divide by 0.0001 or whatever, okay? So that's what we're going to do. We're going to say like h is some small value, like 10 to the negative 5. We add that onto x. We see how much f of x changes, and we divide by that difference h. And that's what we do, okay? So for the gradient, now it's multidimensional. So we have the partial with respect to x1 and the partial with respect to x2, right? So f is a function of x1 and x2. So you have to do this twice, okay? You start by adding h, your 0.0001, to x1, and you leave x2 alone, okay? And you see how much did f change, okay? And you plug in x1 and x2, and you have x1 plus h, and you see how much did f change, and you divide by h, okay? And then you have to do the whole thing again, but this time you leave x1 alone. Don't change x1, and you change x2 by 0.0001, okay? This you put down in your notes, okay? Because I put a question like this on the test last quarter, and a lot of students changed x1 and x2 at the same time. Don't make that mistake, all right? I'm telling you already right now, to avoid the mistake that students did last quarter, all right? Which is they changed x1 and x2 at the same time. You change each one at a time. So if you've got a 3-dimensional vector, you're going to have to do this 3 times. You change x1 by itself, leaving x2 and x3 constant. You change x2 by itself, leaving x1 and x3 the same. And then you change x3 by itself, leaving x1 and x2 constant, okay? So do each thing one at a time, and then you'll get a vector of 2 elements here, or however many elements W is. Is that all right? To get a numeric estimate. So we'll go back and we'll do this, okay? So this was the function that we had earlier, all right? And earlier we found the gradient at -5, 4. So where was it? Okay, so the gradient at -5, 4, we did it mathematically and we found it to be -14 and 22.5, okay? And we did the math and we got -14, 22.5 at 5, 4. Okay, so here we are. And we're going to pretend that we can't do the calculus, okay? We're going to say, I don't know how to do calculus. I don't want to take the derivative, or I'm not confident in my math skills, okay? So we start by plugging in the values, -5 and 4, into our thing. And we can do this. We're confident this. And we get 85, okay? So this is the value of our function right now, 85. Okay, and so what I'm going to do to get the numeric gradient is first I'm going to recalculate the function after I change x1. So I leave x2 alone, I leave that at 4, but I'm going to change x1 from -5 to, what did I do? I changed it from -5 to -4.99, okay? So I leave 4 alone, and I plug this in, okay? And when I do the math, so just assume you did the thing, you get 84.8601. Okay, 84.8601. Okay. The original function when it was -5, 4 is 85. Okay, we take that difference. The difference between this and this is 0.001399. Okay, and so when you divide it by 0.01, you get -13.99. We do this again, okay? But this time I leave -5 alone, so -5 remains the same. And I modify 4 to be 4.01. Okay, so I do the same thing, but twice. First, I leave x2 alone, and I change x1. The second time, I leave x1 alone, and I change x2, okay? And again, a lot of students last quarter changed the 5 and the 4 at the same time, okay? And they got the wrong answer. You can't do that. One at a time, we do this. We calculate what is the value of the function. When I use 4.01 instead, I get 85.22525. The difference there is 0.22525, and when you divide by 0.01, you get 22.525. Yes?
You said something like this was on the exam. Are you allowed calculators for the exam?
Yeah, of course. All right, yeah.
Yeah.
84.8601. Yeah, you don't have to do that by hand, okay? You're going to use the calculator, but I'm just going to force you to do some of these things by hand, because when you have to code it, on the computer, if you don't know what to expect in the first place, because you don't have a concept of what should happen if you were to do this by hand, then you're in trouble, right? And this is like the scary thing about like working and doing like a data science project on your own, is that you don't have answers to check if you're doing it right or wrong, okay? And so we have a lot of these things that we come up with to try to check our own work, right? And this is one way to do it. Okay, and so when we do the numeric gradient estimation, we get negative 13.99 and 22.525, okay? And when we did it analytically, we got negative 14 and 22.5, okay? So we get this and we go, oh, okay, probably I feel like my analytic work was pretty good, okay? And you know, you're gonna get something even closer if normally you wouldn't use 0.01, you would use something like 0.00001 or something like that, like 10 to the negative 5, 10 to the negative 6. You'd use a really small number, and these numbers should be very close to each other, even closer still. And so that's helpful, yeah.
So then it should only differ like by that 0.001, or like that buffer?
Yeah, it differs by a little bit. I don't know if I have a good answer either, okay? I'm trying to think. The truth is even the best computer engineers and computer scientists and mathematicians and statisticians, we're not quite sure what happens inside the computer when you're dealing with floating point numbers. Like, we know stuff happens and it's not the way it should happen with real numbers. And so we're like, okay, we're getting values that are different. Is that close enough? And it's kind of like, if you're getting something on the order of like 10 to the minus 5, 10 to the minus 6 difference, you're probably good, right? And if you're getting something that's different than that, like 0.01 or 0.02 difference or something, and the h that you're using is really small, you're probably doing something wrong. You're probably missing something somewhere along the way. So I know a lot of my answers are, you know, they're not super confident. But I think that's okay, because that's the truth of the nature, right? In statistics, we're always uncertain, so we can do that. Okay, is that all right? Doing a numeric gradient by hand, and this is very useful. I took a online course from Stanford on their neural networks and stuff, and they use this also, because they say, well, here we did the calculus, and the calculus was so hard. I was like, I don't even know how to do this. But they said, yeah, it's hard, so we're gonna check to see if we're gonna do the numeric gradient to see if it was correct. So I was like, well, they do it at Stanford, then we're in good company, right? This was taught by what is it? Andrei Karpathy? Is that his name? Yeah, this guy. So he taught the course, and then he quit Stanford. You're like, well, who quits a job at Stanford teaching? Well, he's the director of AI at Tesla now. So you're like, oh, okay, well, that makes sense. So anyway. And he uses numeric gradient checking, so don't feel bad, right? Okay. All right. Okay. Next topic. This is like Friday of the second week, okay? But now it's Wednesday of the first week, okay? Now we're talking regularization, okay? Who's taken 101C, 101C? Okay, yeah, you were in my 101C class. Okay, no one else has taken 101C. Okay, so have you heard regularization? Okay, all right, this is my first. I will teach you regularization for the first time then. Okay. Oh, shoot. Okay, it's 2:28. We got 20. All right. I'm going to have to continue this on Monday, but we'll do as much as I can right now, and then we'll go on. Okay, overfitting. Have you guys heard of overfitting? Okay, so what is overfitting?
Most predictors. My answer is probably the same thing you wrote right there. It looks like.
Okay, yeah.
But yeah, if you overfit, then like you fit the points you have really well, but another point in the data set is probably not going to be close to the line. So like it's not really a good explanation of the population, just very specific to your data.
Right, so when we overfit, yeah, we are able to predict the data that we have very well, but we might be modeling in our current model stuff that's only exists in our current data set. And it's not something that, yeah, doesn't generalize to the population exactly, okay? And so when we get new data, we do a bad job predicting, right? And so we said, well, one way to avoid that is using cross-validation, right? So we can say like, okay, we're gonna just use only this part of the training data and validate it on this part. And we're gonna do this and do that. So that's one way to kind of tell us if the model that we currently have is overfitting or if it's a good model. So that helps us in model selection. And another tool that we have is regularization, okay? And what regularization does is it changes the loss function to penalize complex models, okay? This is a little bit different, and I didn't mention this in my slides, but in your 101A class, when you do linear regression and you have things like the AIC and BIC, those also penalize complex models, right? The more terms you've got, it lowers your AIC score or something like that. But what's different there is that the coefficients that were found were still found using least squares, okay? We estimated the coefficients using the linear model tool in R or using least squares. We said this is what minimizes the squared errors in our residuals. And then after the fact, after we've estimated those things, let's figure out which one has the best AIC or best BIC or something like that, okay? Here, with regularization, we modify the loss function directly. So the coefficients we estimate are not going to be the values you get from least squares regression. They're going to be different, okay? Did you guys learn about the BLUE, B-L-U-E, in your, which class? 100C. Okay. So if you've taken 100C, you've learned about the BLUE. And if you haven't taken 100C, this makes no sense. But the idea is, like, we like least squares regression a lot, right? We like to use OLS for a lot of things because there's all these different properties, and one of them is that it's the BLUE. It's the best linear unbiased estimator, right? Okay. Yeah. So it's got these nice properties, and you know, you have to do all of this derivation and proving that this is the loop that shows the least amount, blah 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 blah. Okay. But when you do OLS, you get the unbiased estimators, okay? When you do some regularization, you actually end up getting biased estimators, okay? And you feel like, oh, biased estimators, that doesn't sound good. I don't want that. But actually, it could be a good thing, all right? So let's just back this up, and we'll cover this idea of modifying the loss function, okay? Okay, so for OLS regression, okay, we say we want the model that minimizes the total squared error or the mean squared error, right? And we said we can find it this way. We said, you know, basically our actual values minus our predicted values, we square them up and we sum them. which I hope, I guess it's only your second day in class, but maybe I've shown you this enough times for you to recognize this to be the sum of squared residuals or the mean squared residual if I have the 1 over n. Is this okay by now? Okay, in matrix notation. Okay. And so we said the model that's the best is the thing that minimizes this thing, right? So if we're going to minimize the mean squared error, ordinary least squares regression says we're going to try to minimize this. And we get our slope and we get our intercept, we get our coefficients this way. Okay. What we're going to do now is we're going to say, you know what? If I minimize this, I always end up wanting to add more predictors into my model, right? Because if I add another predictor, I can minimize this even more. If I add another predictor, I can get this even lower. So let's just add all the predictors I have, right? And that's going to lower this thing as much as possible. And so we say, well, yeah, that doesn't sound right. I don't want to add 50 predictors when 3 of them is good enough. So you know what? Let's make a penalty for how complex the model is. Okay, so before I add another thing, okay, or if I add another thing, we're going to change the loss function. The loss function is going to get bigger by this complexity measure, okay? Or we just call it a penalty or something, right? And so this L prime we're going to say is the regularized loss function. So this is this is the normal, ordinary. I'll call this the ordinary loss function. And when you add this thing, it becomes the regularization, okay? And this lambda is how much weight to put on the complexity parameter, or complexity penalty. Okay, so maybe I'll just provide us kind of an analog to real life, all right? So here we have kind of 2 competing goals. We've got this part represents the least squares regression part, the least squares mean squared error here, this part, and this is a complexity parameter, where this is going to say more complex models are better, and this is going to say less complex models are better. Okay, so we've got kind of these 2 competing things, and we've combined them. Right? So we often have similar things in real life, all right? And this is just this overly simplified view of life. Okay, all right. So one day you'll probably have to look for a place to live. Okay, all right. And so let's say you're considering apartments. All right, and so one apartment is $2,000 a month. And is a 5-minute commute from your job, all right? I don't know, maybe you can afford this apartment, maybe not, right? And then the other apartment is $1,800 a month, but the commute is 45 minutes each way, right? Okay, so which apartment do you pick, right? If money is the only factor that matters, right, then you're gonna go with the cheaper apartment, right? If money is the only factor, right, then the decision is easy, okay? But most people value their time, right? And you have to say, well, is it worth it to me $200 a month to save, what is it, 40 times 2, 80 minutes a day on commute? Okay, and some people will say, yeah, absolutely. And other people will say, well, I would have just spent that time playing video games anyway, so, well, maybe that time is valuable or something, You have to kind of decide whether the extra money or and depending on your financial situation and what your social life and what everything else looks like, people will have different answers, right? So some people will say, oh yeah, definitely I want to save time and I'll spend the extra money. And other people will say, well, I don't mind sitting in traffic. I like listening to my podcasts, and it's like me time. I don't have road rage. It's very relaxing sitting in the car. And I save money, and I don't have to talk to anybody else for an extra 45 minutes a day. This sounds great. There's no loss here, Except maybe my carbon footprint's a little bit bigger, but I don't know. Okay. Anyway, so you got different things going on, right? And so so the true cost of the apartment comes down to the rent, and then you have something that is going to be different for everybody. It's like your preference factor multiplied by the commute penalty, right? And so if you have a strong preference against commuting, like you hate commuting, you like every time you get in the car it makes you angry or something, like then the preference factor is going to be high, all right? And you really want to minimize this commute penalty, and you're willing to pay extra rent to kind of avoid this. And on the other hand, if you're like, there's basically no penalty at all for living far away from work, then you'll go with the lower rent type of thing, okay? And so this is kind of what we have. We've got this lambda term back here that will kind of say, like, is it worse, like it's really bad to have a complex model, or it's just only kind of bad to have a complex model, okay? And so that's what we have here. Is that all right? Does that kind of make sense? All right. Okay. So with this thing, one issue is that we're not actually comparing this apartment to another apartment or this model to another model, okay? Because that's what AIC does. It compares different models. But here we are just saying, how are we going to pick the best coefficients, right? So how do I pick my best, not beta coefficients, but W0 and W1 and W2 coefficients? And here we're going to say the best W coefficients that we're going to pick are the ones that minimize this modified loss function, okay? It's not going to be, we're not just going for least squares anymore. We're trying to get this modified regularized loss function instead. Okay? So, so that's what we're going to do. So, okay. So, so this is what we have, okay? We've got our modified, our regularized least squares, I can't read, our regularized least squares loss function, okay? So this is just the regular, ordinary least squares loss function plus some complexity parameter, okay? And complexity is maybe not the best word, but that's what we're using here, okay? And so the question is, how are we supposed to measure a model's complexity, okay? How do we measure this? Okay, and so here are two models that we can think about, and we can think about how do we measure the model's complexity, okay? And so one is going to be fitting a fourth order polynomial versus a fifth order polynomial. And so the fourth order polynomial looks like this, okay? Blah, 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 okay? I'm sorry, wait, what did I do? Okay, so if we do a fifth order polynomial, it looks like this. And the fifth order and the fourth order polynomial, I think I have these labeled incorrectly. Sorry, I got to switch that up. The fifth order and the fourth order polynomial are exactly the same, except we've just said W5 is a 0. Okay, and if we force W5 to be a 0, then we've got a fourth order polynomial. Okay, and so one way to count complexity is just to say, well, how many non-zero coefficients do we have? How many non-zero coefficients do we have? Okay, and this is known as the are you guys familiar with like the L0 and L1 and L2 norms of a vector? Kind of familiar, kind of ringing bells? Okay, so the L0 norm is how many things that are not zero, okay? All right, it turns out if we try to do with the L0 norm, it's like really hard because it's like not smooth, and so trying to optimize this, there's no derivative that even exists because it's just flipping switches on and off, and it's discontinuous. We can't do it. It gets computationally really hard to do, okay? So, So almost nobody does this because it's very impractical. It would be nice if we could, but computationally we don't have a way to do it. Okay. So so we said, well, instead of just counting how many non-zero coefficients we have, let's look at the absolute values of the coefficients. Okay. All right. And this is weird, okay? But it also kind of makes sense as a measure of the complexity of the model, okay? So if it's 0, if the coefficient is 0, it's not going to contribute anything to the complexity of the model, okay? And if the coefficient is not 0, it contributes to this penalty factor, okay? And if the coefficients get bigger, then it contributes more to this penalty factor. So what does that mean? It means, like, if we just think of the coefficient, and this is not necessarily 100% accurate, but if we think of the coefficient as kind of a scale of how important this vector is, where bigger coefficients represent like vectors that are more variables that are more important. Having a bunch of these large coefficients represent a model where you think a lot of variables are really important, and maybe that kind of represents a more complex model. Okay, there's some major implications of like whether you should scale your data or not, because that's going to have a significant impact on this, and so we can talk about that later. So basically, when we do something like this, we're going to say that if we introduce a W or increase W, then it has to improve our least squares values. It has to improve our sum of squared errors at least by a factor of lambda times whatever change we're inducing in W. Okay, this is known as lasso. Okay, have you guys heard of lasso? Okay, other than the 101C students that I've had. Okay, so lasso uses this as a complexity parameter. Okay, it's the absolute values of the elements in W. Okay. We'll probably run out of time here. And then the other is that, well, instead of the absolute values, let's look at the squared values. Okay, and so this is the W2 norm squared, so it's the squared elements in W. And again, if W is 0, it contributes nothing to the penalty, and values of W that are bigger contribute more. Okay, the difference here with ridge regression is that bigger values of W are more heavily penalized than small values of W. So if W is less than 1, it contributes a lot less of the penalty, right? If W is like 0.5, 0.5 squared is 0.25, and that's a lot less, right? But if W is 10, 10 squared is 100, it's contributing a lot more to its penalty. Okay, yeah?
Don't we kind of want big values in our coefficients? I mean, it seems like small values in the coefficients implies a bunch of like questionable variables. If we've got like 5 really big ones, it seems like that could really give us a big penalty, even though we kind of want that, right?
So yeah, let me address this later when we talk about scaling the things. And again, we're not just, this is not the only thing we're looking at. This is just a way to measure some kind of penalty, okay? We're still trying to minimize the sum of squares or the mean squared errors, okay? That's still what we're trying to minimize. But now we're also just including kind of this extra penalty if we have a bunch of coefficients that are non-zero or a bunch of coefficients that are quite large, okay? And so, you know, the answer, everything depends, and maybe some graphs will help clear some of this up a little bit. But this is just to kind of introduce the idea of changing the loss function. So we're still minimizing the sum of squares, or the mean squared errors, but it's not just that only. It's the sum of squared errors plus some kind of penalty, okay? So when you're searching for your apartments or whatever, you're trying to minimize not just the rent that you have to pay, but also maybe the commute time, depending on your preference, okay? And so so that's what we've got going on, all right? And what this will do is it will change the kinds of coefficients we end up selecting for W. Do our W's end up big or small? And it's gonna change that, okay? And so when you use the squared values of W, that's known as ridge regression, okay? All right, so we'll pause here for now, okay? And I'll finish up this concept of regularization next week. Please get started on your homework, and we'll see you guys on Monday.